First quiz question asks if you have an object excuse me, with a 2 meter per second upward velocity, how high is it going to rise before it starts to fall back down? Well, if you think about it, the object is going to rise until it comes to rest for an instant before it starts to come back down. So its initial velocity is going to be 2 meters per second. Its final velocity during that interval from the start to reaching its maximum height is going to be, the final velocity is going to be 0. And the acceleration is negative 9.8 meters per second squared, but I round that to negative 10 meters per second squared for ease of calculation. And it's legal to do this unless we say otherwise. Okay, so what can we determine from this? Well, we don't need the equations of motion, although I use them over here. I'm going to reason it out without the equations of motion. Okay, what can we get from two of these quantities, initial velocity, acceleration, and final velocity? Well, initial velocity and acceleration doesn't tell us anything. Acceleration and final velocity doesn't tell us anything, but initial and final velocity does. From the initial and final velocity in the straight line property of the right of the v versus t graph, we know that the average velocity is the average of the initial and final velocities. And let me put a plug in here. I'm still seeing people do final minus initial divided by 2. You don't average two velocities to get an average velocity. You don't average two velocities by subtracting them and dividing by 2. You average two velocities by adding them and dividing by 2. So we want to be sure we understand why this is so, and we want to not make that mistake, okay? So, in any case, that's how we're going to reason it out. Now in yellow over here, I've done the calculations, but I just want to get the reasoning process. Okay, what else? From V0 and VF, we can get the change in velocity. VF minus V0 is the change in velocity, just by the definition of delta, change in. Okay, then that leaves us just delta S and delta T, because as soon as we've got V bar and delta V, along with the 3 given quantities, we know 5 of our 7 quantities, leaving just 2, delta S and delta T. So I listed those, and it turns out that delta T is the first one we can determine. We still can't determine delta S from the quantities above here, but we can determine delta T just from the definition of average acceleration. Average acceleration is the average rate of change of velocity. I almost said it wrong. Average rate of change of velocity with respect to clock time, which is change in velocity divided, excuse me, by change in clock time. So the acceleration is delta V divided by delta T, but we do a simple arrangement of that, and we find that delta T is delta V over A, change in velocity divided by acceleration. Okay, so we're going to be able to calculate delta T, and then we put that back in here, combining that with the average velocity that we know in terms of the definition of average velocity as the average rate of change of position with respect to clock time, delta S divided by delta T. We see that we can multiply average velocity by delta T to get our displacement delta S. Okay, well, we plug our numbers in. Now VF plus V0 over 2, the average of 2 meters per second and 0 meters per second is clearly 1 meter per second. So that's very straightforward. Delta V, subtract the final velocity, the initial velocity from the final, subtract initial from final. We got subtracting 2 meters per second from 0 meters per second, we get negative 2 meter per second change in velocity. This thing's going 2 meters per second. At the end, it's at 0 meters per second, so the change was negative 2 meters per second. That's very intuitive, but we also want to check it out in terms of the expressions, okay? Then delta T, delta V over A, well, we got delta V here, we got the acceleration. We can divide the negative 2 meter per second change in velocity by the negative 10 meter per second squared acceleration, and we get 0.2 seconds. The units, I'm not going through those calculations now. I've done that plenty of times, and it's not that I don't want to do it now. I'd be glad to, but I don't want to take up your time with something you should already know and really need to review if you don't. So meters per second divided by meters per second squared does give us seconds. You need to invert the meter per second squared multiplied by the meter per second, and so forth. Okay, so there we have it. There's our delta t, and then we can plug that in here, multiply our delta t, which is 0.2 seconds, by our average velocity, which is 1 meter per second, to get a displacement of 0.2 meters. And we've solved the problem, and we've concluded that the object will rise 0.2 of a meter, 20 centimeters, about from here to here. Okay. Now, if we wanted to use the equations, we could equally well have done that. And if I don't specify, you're welcome to do it either way, but I will often specify. Do this by the equations, or do this by pairing up your quantities by direct reasoning from the definitions of average velocity, average acceleration, and the straight line property of the real graph, of the v versus t graph. Okay, we list the equations of motion, and you need to be able to do this. I did a digression here. Think about the units. The a delta t squared and the a delta s are confusing. Okay, it's hard to remember and keep those straight. You'll know you have them straight if the units work out. What are the units of a times delta t? Okay, units of acceleration are meters per second squared. Units of delta t are seconds. You multiply meters per second squared by seconds, you get meters per second. What's the unit of squared velocity? It's the square of the velocity unit. The velocity unit being meters per second, the squared velocity has units of meters squared per second squared. That does not match the units of this term or the units of this term. Now, you can't add meters per second, which would be the units you had here if you put a delta t in there accidentally, with a quantity that's in meters squared per second squared. That would make no more sense than adding miles to hours, okay, or years, okay. I've got 10, what's 10 years plus 87 miles? They aren't like terms. They don't measure the same thing. They can't be added, nor can the meters per second that you would get here if you use delta t be added to the meters squared per second squared you get here, and you certainly wouldn't add meters per second to anything to get meters squared per second squared over here. So if you accidentally put a delta t here, the units are going to tell you that you screwed up. Go back and fix it. And if you put a delta t squared here, your units would still be messed up. Or if you put a delta s up here, or even worse, a delta s squared, the units would not match the units of the rest of the equation. So that's a very important idea to understand. Now I'm going to go on with the solution in terms of the equations in a separate video, since this one's running a little bit long now.